Hello and welcome to Soil Moisture 201, Water Content Measurement and Theory and Application. My name is Colin Campbell. I'm a research scientist here at Decagon Devices, and in this virtual seminar I hope to take you through several things that we've come to understand about measuring soil water content, both in the way it is measured and some possible applications for you as you're trying to understand the natural environment. Now today, just as a general outline, we're going to start off by talking about indirect versus direct measurements in the field. Now we have to understand this to be able to go and talk about the many different methods and compare them so we really understand what is best for your research. Next, we're going to talk about the difference between a gravimetric water content measurement and a volumetric water content measurement. Now in the literature, oftentimes it's stated we measured water content, and there's really no explanation of what technique they used or what type of water content it was until you look at the figures and you see, well, it's grams per gram or meters cubed per meter cubed, and there you can make a determination for yourself. Oh, this was volumetric or this was gravimetric. So we're going to talk about exactly what those are. Then we're going to get into the actual measurements themselves and go through and talk about measuring the water content. What techniques are out there and available? First, we'll talk about direct technique. Then we'll go through and talk about all of the indirect techniques. And finally, we'll kind of gather those things together, talk about installing sensors in the field just briefly, and then go through some applications that we here at Decagon have experienced and may be helpful to you. So first, let's discuss the difference between direct and indirect measurements. Direct measurements are those where we can sense a property directly. Now, these might be somewhat similar to this scale here up in the corner. Now the scale has some candy there in a weighing pan, and we balance the unknown weight of that candy across a center beam with some known weight that we can move around on that bar. And once those are in balance, we know the weight of the candy because we know the weight that's on the other side of that center beam. We call that a direct measurement. Now indirect measurements are something where we infer a property that we don't know from a property that we can measure. Now, if you look here at this thermometer, we all are familiar with thermometers, but rarely do we think, hey, I wonder if this thermometer is measuring temperature directly. Well, it's not. It's measuring the expansion of an alcohol inside a sealed glass tube. And we have calibrated the expansion of that alcohol in some scale that we then understand, then have set to this known standard we call temperature. So we have tied those two together. Rarely do we think, oh, well, we haven't measured temperature correctly when we make this indirect measurement, but we do understand that because we're not measuring temperature directly, that we have to take steps relating first the expansion of alcohol in a sealed tube to this temperature value. Now, what does that have to do with water content? Well, I'll get to that in just a minute. So wait a second while we talk about the two different types of water contents. The most familiar to many is volumetric water content. Volumetric water content is simply the volume of water divided by the total volume of sample. So here we have a sample of soil that's been sampled in the field. Now, when this was taken out, if we could actually, by some means that isn't available to us, separate them into the constituent parts right here, we might have in this particular sample 50% soil minerals, 35% water, and 15% air. Well, from that sample, we can say that it would have 35% volumetric water content. Now, if we then consider gravimetric water content. Gravimetric water content is given by the mass of water divided by the mass of dry solids. And I've just shown this here as kind of the balance between that water weight and the dry weight of those materials. This is our gravimetric water content. And we are familiar with this one because it is really the the easiest thing to measure in the lab. But how do we convert between the two of these? Well, they are converted just by the bulk density. If we take the bulk density, which is the mass of the dry solids divided by the total volume of the sample, we can convert from one to the other. Now, this is important because it brings up two important points before we go on that we must understand as we prepare ourselves to talk about measurements of water content. In situ measurements, meaning the things that we can measure when we go to the field, these methods can only measure volumetric water content. There are no methods that I'm aware of in the field that measure in situ that measure gravimetric water content. That's a laboratory method and it's only done in one way, which we'll talk about in a moment. Now, this brings up the other important point that if you really would like to calibrate or get volumetric water content in the field, you must, at the same time you sample, instead of just going and taking a small trowel and a bag and shoveling out the soil into this bag and taking it back into the lab, as we'll talk about in a moment, you must know the volume of that soil. So you need to use a known volume sampler, stick it into the soil to get that known volume to actually finally evaluate the volumetric water content. So we'll quickly step now into discussing the different measurement types. And the first one we have to start with is the gravimetric method. The method by which all other methods, as we'll talk about, are calibrated to, because the gravimetric method is our standard. In this slide, we can see that there are basically 4 steps to this that are very simple. Many of you have already done this. First, we go to the field and take a soil sample, as I just mentioned. I'm showing here a volume sampler that we use in the lab to actually take these samples. You might want to take a larger volume in the field, but regardless, if we take a known volume when we take that soil measurement, we can then calculate the volumetric water content when we're done. But anyway, we take our soil sample, we put it on a scale to get the mass of the soil and water and whatever else is in there. We put it in the oven, we dry it for 24 hours at 105 degrees C. Then we take that sample out. We, of course, let it cool, making sure not to gain any water during that process. And again, we weigh it on a precision balance. And again, to get volumetric water content, as long as we know the volume of soil that we sampled, then we can easily calculate that. Now, just as a general note, we are going to have to use this to calibrate all other techniques. And there are application notes online available. Certainly from our website at Decagon.com, you can go in and search for an application note on calibration, and you can actually get step-by-step instructions on how to do this. With each technique we talk about, I'm going to briefly discuss some of the advantages and disadvantages after I get done talking about the theory behind it. With the gravimetric method, there are several advantages, including that it's very simple to do, that it's a direct measurement, it's the only direct measurement that we have, and of course if you have an oven and a scale, it's going to be the least expensive in terms of the things that you need to buy. Now, the disadvantages are primarily that it's destructive. Anytime in research that you want to measure something, but to do that you have to destroy the thing you're interested in measuring, there are some obvious disadvantages to that. Also, to do this is time consuming. Often we don't want to take just one sample of water content. We want to take a lot of samples. And to run a lot of samples through the oven does take quite a bit of time. And finally, if you don't have them in your lab available, of course, you're going to have to buy a precision balance to make those careful weight measurements and an oven to run this technique. Now we're going to quickly step on into other techniques, because my guess is you probably know all about the gravimetric technique and are quite familiar with making measurements on a scale. But what about all those other ones I mentioned at first? All these measurements are indirect. That means we're taking a property that we can measure and we're inferring a property that's more difficult to measure. And we're going to start with neutron thermalization. We're going to talk about the dual needle heat pulse probe, and then finally talk about the measurement of dielectric permittivity, and talk about how all these are related to volumetric water content. So let's jump in first and talk about the neutron thermalization probe and discuss how it works. Now, this is one of the older techniques in terms of field measurements that we have used to measure volumetric water content. What happens is we have a small radioactive source in this instrument that is emitting into the soil these epithermal neutrons that are escaping out of the source, going into the soil, and interacting with the soil as they move. Some of the neutrons that are emitted will interact with hydrogen atoms, and when that happens, those neutrons are then slowed. And the fact that they are slowed in this interaction can be useful to us, because with a detector, some of those neutrons, now called thermal neutrons, when they interact with the hydrogen atoms, they can be detected, and the amount of thermal or thermalized neutrons then can be related to the amount of hydrogen atoms in the soil. And because hydrogen is most closely associated with water, at least the things that are changing in that soil, then we can relate the amount of thermalized neutrons to the volumetric water content in the soil. And you can see here on this graph what's been done. This is a graph that was given to me by some friends down at Texas A&M University. They were calibrating their neutron probe in a lot of different soils. And here on the screen we're showing a calibration. So here, if you look, you can see down here calibrations for a sand and a silt here in the squares, and all the way up top, a little harder to see, are some yellow triangles, which is clay. Now you notice that although very similar in this calibration, that all the soils are not the same in terms of their calibrations. So they had to make some soil-specific calibrations for their silt, sand and silt, which were fairly similar, and then their clay, which was different from the sand and silt. But they were able to relate the count of those thermalized neutrons there on the x-axis to their volumetric water content on the y-axis. Now you have to remember that as you do this, you can make site-specific calibrations. What they used to do is go out in the field, they install, as I'll talk about in a minute, an access tube, install their access tube for their neutron probe, make measurements at one location, and then take gravimetric measurements surrounding that neutron probe installation sleeve, and then they were able to make these calibrations. So how did they actually make the measurements? Well, after you install this sleeve into the soil where you're going to put your neutron probe into the ground, you're going to go back to that sleeve, you're going to uncap it. You got to cap those things to make sure they don't fill with water. You lower your neutron probe to each depth that you want to make a measurement, and then each measurement takes between 14 seconds and 2 minutes to make. They found, as I recall, between 30 and 45 seconds were good enough that they didn't have to stay at each site too long because they had a lot of measurements to make, but that their accuracy was acceptable. And the longer the time you wait to get a good value, the better accuracy you get. Now, there are several advantages and disadvantages to this sensor. This neutron probe has the largest volume of influence of anything that we're going to talk about today. When the soil is dry, the volume of influence looks something like a volleyball. Now, as the soil wets up, that area of influence tends to get smaller and smaller till we get something somewhat larger than a softball when the soil is near saturation. But this is the best volume of influence of any of the sensors we're going to talk about today. One of the nice things about that is that it gets away from some of the problems with spatial variability that we might see in some of the other measurements that we'll talk about. Now, a single measurement can also go and measure lots of sites across a field or even wherever you want to take this. So if you buy one neutron probe, it can work for anywhere. And different from a couple of the other measurements we'll talk about today, salinity and temperature are not an issue for the neutron probe. Now, going on the disadvantage side, there are considerable disadvantages to this technique, which is why a lot of these other measurements have come along. First of all, you can't obtain a continuous record using neutron thermalization. Why? Because it is something that's regulated by most governments of the world. Because it's using a radioactive source, you cannot leave it in the field. It's got to be under constant supervision, whether it's under lock and key at the lab or out in the field. If you don't have it, it must be locked in your vehicle. So there's no way just to leave it out in the field and get continuous monitoring. It also requires radiation certification to use, and again, because you're using this radioactive source. Instruments are also quite expensive, and so it can be challenging to purchase one of these instruments, and they're rather heavy, difficult to move around, and time-consuming to make all these measurements. So a good option, but there are other things that we can talk about. Now, just a quick note on emerging technologies. The atmosphere naturally has these epithermal neutrons occurring around, and some of the new techniques that have been developed use these natural epithermal neutrons as they go into the soil, interact with the hydrogen atoms, and are available to detect. This new technology is able to compare the difference of thermalized neutrons coming in from the atmosphere and coming out from the soil, and be able to make an estimation of soil moisture over quite a large footprint. This technology is called Cosmos, and you might look up on the web to get a little more information on that. Now, the next sensor we're going to talk about is the dual needle heat pulse probe. Now, we go from the largest volume of influence all the way down to the smallest volume of influence. And let me tell you about this sensor. The theory behind it is that changes in the heat capacity or the heat storing ability of the soil are strongly dependent on the water content. And that probably makes a lot of sense. So we can create a calibration that relates the ability to store heat of that soil to the volumetric water content. This measurement is reasonably simple, and I have a little diagram here at the bottom of the slide where we have a heater here that is heating the soil for 8 seconds, and a needle that is 6 millimeters away measures that heat pulse as it comes from that first needle, and the maximum temperature recorded is related, or this delta T is related to the volumetric water content and the heat capacity of the soil. Now, the installation of these sensors is relatively simple. We just have to push them into the soil, but we have to be very careful. The needle spacing is crucial to get this measurement right. A needle deflection of 1 millimeter causes a 6% error in measurement of the volumetric water content. So you can imagine that pushing these into even soil that has very small stones in it could be a bit of a problem. These also can be connected up to data loggers and then run continuously over time, so we can get a continuous measurement of soil moisture over time. Now, they've had several advantages and several disadvantages. The first advantage to them is that they have a small volume of influence. And maybe you're saying, hey, wait a second, you just mentioned how important it was to have that large volume of influence because we want to make sure to to not struggle with the spatial variability of soil moisture across a field. And that's absolutely true. But there are some cases where we'd really like to know the soil moisture in very small volumes. Think of a desert crust where we're trying to figure out whether or not there's water available or water present in that crust that might be useful for growth of some kind of organisms. Well, these would be the only probe that you could use to measure that desert crust. And that's been done in the paper that I note there at the bottom of the slide. Now, the other opportunity you have is to look at things that are growing. Imagine trying to understand the amount of water right at the growing surface of a seed or a root. These sensors would allow you to be able to do it where none of the other techniques that we'll talk about really would be good for this use. Now, I mentioned in the last slide about hooking these up to data loggers. And to use the dual needle heat pulse probe, you must hook them up to precise data loggers, which can make this measurement a little more expensive. They are also susceptible to temperature gradients. Now, I mentioned this desert crust, and maybe you're excited thinking that we could finally make a measurement in that nice little crust. But we're in the desert, and temperature fluctuations are crazy there, as you understand, with high daytime radiation load and low nighttime temperatures as we have clear night skies. This paper that I note at the bottom of the slide also goes through to correct all these diurnal variations in temperature and show you how to get the best measurements from these sensors. But I can tell you it's not easy. Now, of course, if integrating a very small volume of measurement isn't your goal, then that is certainly a disadvantage to this sensor. And as I mentioned, the deflection of these needles is a real challenge when installing them in soil, so their fragile nature is something that needs to be taken into consideration. Now let's move on to probably the most popular technique today for measuring soil moisture, which is the electromagnetic measurement to measure the charge storage in soil. And we're going to step through this by first introducing you to basic theory behind electromagnetic waves, and then we're going to talk about the two different types of measurements that are available. Now, I imagine back when you were in middle school sometime, or even in grade school, your teacher came around and handed you a magnet with some iron filings and said, play with these for a little while. I remember it. I took those iron filings, dumped them on the desk, and put the magnet right in the middle because I was pretty curious what would go on. Now I was amazed to find out that didn't work at all because the magnets covered the whole north and south pole of the iron filings covered it, and I wasn't able to see anything. But when I got that whole experiment sorted out and finally put the magnet in the right place, I found these beautiful electromagnetic lines forming around the north and south pole of the magnet. Now, what I was interested to learn was that even though I couldn't see it, there was a field that was created, and those lines were part of this electromagnetic field. Now, as we've grown and understood electricity better, we realize that if we create a positive and negative charge, not from a magnet now, but from being able to add electrons across a open space, or on two sides of metal across an open space, we find that we can form the same electromagnetic field. We also find that when you put things between those two metal electrodes, that whatever is in the middle will tend to store that electromagnetic field for a period of time. And we call that material, as I've noted here, the dielectric material. And when it's put in the middle of this positive and negative electrode, we then have a charge storing area, or what we often call a capacitor. Now, it's interesting that we've discovered things about different materials these properties of interest that there are many different materials, obviously, and they store quite a range of charges. From air, which was arbitrarily set as to have a dielectric permittivity or a charge storing ability of 1, and then several other things that we might consider in nature, like organic matter, which is about 1 to 5, soil minerals, 2 to 5, ice is about 5, and then you look across the spectrum and see that water has a very interesting ability to store charge because it's a polar molecule. It has an arbitrary value, or a relative value, not arbitrary of course, but relative value of 80. And so it can store a lot more charge than any other things that I've noted here. And of course you can tell that all these materials are things that we can find in soil. If we mix soil all together, you think about the fact that we have all these things in there: air, soil minerals, organic matter. Some of you have ice in soil, others do not around here. We have quite a bit of ice in the soil various times of the year. And then we have water. And as we look at a little range that I've put together here, we go from a dry soil that would be really only organic matter, air, and soil minerals around 2 to 3 in dielectric permittivity, all the way up as we have the water begin to fill the pores to a dielectric permittivity of, let's say, 40. Now this is not a fixed value, but let me just make a note here that will hopefully clarify this whole idea. Now in soil, if we have a soil out in a natural environment, we can pretty much count on the fact that the organic matter, the soil minerals, those are going to stay to a great degree relatively constant. But what's going to be changing is the air and the water fraction. And since air stores almost no charge on this continuum, and water stores the bulk of all the charges in that soil, if we measure the change in this charge storing capacity or the change in the dielectric permittivity of that soil, we can infer something about the amount of water in the soil. And that idea caught hold across the science back in the mid-70s, and we'll talk about that in a minute. But the idea is, the take-home message is that the total charge storing ability, or in this equation, the epsilon sub t to the b power here, is related to the charge storing ability of each constituent times the volume fraction of each constituent. And when we sum all these together, we notice, by the way, that there's theta, the volumetric water content summing here. When you sum all these things together, we get the total charge storing ability of everything in the soil. If we rearrange this equation, then we can put it in terms of what we're really interested in, which is the volumetric water content. And then ideally, it would be a first order function of the dielectric permittivity. But as you notice here, that this relationship is generally a second order relationship in the real world. So the take-home message is quite simple. Anything that can measure the dielectric permittivity of any media should be able to be calibrated to measure volumetric water content. Now, the person who really put this together for soil science was Dr. Clark Topp, who I just threw his picture up here in this slide. He came and visited here at Decagon a couple of years ago, and there he and my father Galen are sitting down reading one of his articles talking about how this calibration is done. What is this relationship between the charge storing capacity and the volumetric water content? And here in this graph, if you look over, you can see that here I've just taken what I drew in a couple of slides ago, water going from let's say oven dry all the way to saturation here, and there's a relationship with the total dielectric permittivity now to the square root. Now there's a famous equation in the literature that we always talk about, which is Topp's equation. And this is what he generated back in 1980 to show soil scientists and many, many others that we could develop a relationship between this charge storing capacity and the volumetric water content. And when we talked about this equation, he said, you know, over the years, I actually have tended to prefer just a square root equation, one that I'm showing on this side, to my original TOPS equation. So we actually, when we've done these calibrations, we've tried to move in this direction and found a better fit. So we have the volumetric water content is equal to some parameter alpha times the square root of the total charge storing capacity, the dielectric permittivity, minus, or this A times the square root of epsilon T minus B. And those A and B, he showed in that original paper, although it didn't use this equation, were pretty consistent for a lot of different soils, but not all of them. And I've noted on the bottom of the slide there that we have problems sometimes measuring in high electrical conductivity, high clay activity, and sometimes even temperature and bulk density can affect this relationship, this A and B, these empirical constants. Let's make a brief mention of volume of sensitivity of these dielectric sensors before we jump in and talk about the various types. Now, the basic principle behind this is that just like I showed you with those magnets, the highest sensitivity of these electromagnetic fields that we produce is closest to the surface. That electromagnetic field, although it goes out to theoretically infinity, falls off quickly with the distance from those surfaces. The second idea is that we can design sensors that can increase this volume of influence, but only to a point. So we can change the rod spacing, we can increase this volume of influence, but wider needle spacing only increases it to a certain point. And the volume of influence for most of these sensors, these dielectric sensors that we can talk about that are so readily available, tends to be from, let's say, 1 to 2 centimeters from the surface to no more than 4 or 5 in my experience of testing them in the lab. When we talk about dielectric measurements, there are basically 2 different measurement techniques, and I can tell you that they're often confused when you go out and look on the internet. In fact, some manufacturers report that their sensors are in fact one type of sensor when they're in fact another. And therefore, we should really judge a sensor based on how it performs and how accurately it measures soil water content, and not really pay too much attention to what people are saying of what particular type it is. But we're going to get in and talk about some of these sensors. First, the time domain reflectometry sensors, and second, frequency domain. So first of all, time domain reflectometry. My friend Kosuke Noborio, he and I went to graduate school together, and to try to help us as graduate students back in the 90s understand this new idea, at least new to us, of time domain reflectometry, he went out and he wrote up a very nice introductory paper. And I asked him the other day if he actually had this around, and he said he didn't. But if you really want to get a good basic knowledge of this, you can always email me, and I'll go ahead and send you, he said it was all right to send you this introduction to TDR, and then you can sit down and read this and get some good information on it. But let me try to explain what he showed in this paper in just a couple of slides. So here I'm going to first say we have this generator that generates a pulse, a voltage pulse that we're going to send down a cable. Now, can I just say that initially this technology was used to hook up to cables to power lines to try to figure out where power lines were broken. So these electric company workers needed to find out when they had where the cable was broken when they lost power somewhere. Instead of going and checking all these cables, they'd use these testers to sit down and send a pulse of energy out these cables, and the reflection, the time it took for this energy to go out, reflect out the end of the cable and come back, would tell them exactly where this was. And Clark Topp and friends thought, well, I wonder if this would work for measuring soil moisture, because they knew that the speed that this pulse traveled was slowed as the charge storing ability of material around this cable increased. Okay? And so he decided to try to test this out. And this is the cool thing that he found. So this pulse generator produces a pulse of electromagnetic radiation, and that you can see right here. Travels down this cable. See if we can get it to go down there. There we go. Reflects off the end and comes back. Now obviously as soil scientists we don't really want to know anything about this cable. Or I suppose we could and try to integrate it in, but it's far better to, for our purposes, to look at this probe right here. When that energy hits the front of this probe, it produces a little reflection, and we'll talk about this in a minute. It's right here. As it passes along this sensor and hits the end of the cable right here, it also produces a reflection of energy. And the time that it takes for that energy to hit from the beginning of this probe to the end of the probe, we can use to calculate the dielectric permittivity. And let me show you how that's done now. Let me just back up again. Here's that pulse of energy going down, reflects off the end, and it goes back into this sampling oscilloscope that basically looks at this pulse of energy, the energy charge from that reflection. And here we go. We're going to look at this, what we might see on the sampling oscilloscope comes, then it hits the front of the probe. Again, let's see that again. Hits the front of the probe, the end of the probe, and the time it takes to travel along that probe is related to the charge storage of that material that's around the sensor. And in our case, as I mentioned before, it's mostly due to the charge storing, the water in the soil that's producing all the charge storing capacity. So here's what Kosuke put together to show several examples of this. Again, we're looking at a sampling oscilloscope. This is the idea of the length here. This is the reflection coefficient, or the reflectance of that pulse. Here we are at the start of the probe. It's reflecting off the start here. And now we have air-dry sand. Front and end of the probe, you can see how short that is because there's very little charge storing ability, so it's very, very quick to get that pulse along. Here we have water saturated sand. You can see how that time is extended, and finally we have distilled water. And again, that length is much, much longer. So you can see that as we add more water to the soil, that we increase this apparent length, the time it took the pulse to actually get down the sensor, and we can compare that to the actual length. In the end, we can relate that to the charge storing ability, and finally the volumetric water content. So that's how it all works. And you're more than welcome, like I say, to email me, and I can send you this very nice introductory article if that's something that interests you. Now, what are some of the challenges to TDR? Well, TDR is actually a great way to measure water content. Why can't we use it everywhere? It actually does work very, very well. It suffers in the high clays. That's been well documented more recently in literature. There was a feeling at one time that it works in every soil anywhere, but that we really know is not true. There are some areas where we need to do another calibration, but with a better calibration and better analysis techniques, especially that are starting to appear in the literature now, we can get good values out of this measurement, even in those difficult conditions. But why move on? Cost. These systems are quite expensive, and so if you want to put out a lot of measurements across a field, it becomes quite difficult to use one of these systems because you have to spend a lot of money on cabling because you don't want to buy more than maybe one central unit. You have to spend a lot of money on sensors, etc. There's also complexity. These systems are very complex because of the very good technology that's used inside them. And so setting up systems and maintaining them creates challenges. Finally, power consumption. These do require more power to run, and so will require things in the field like solar panels and batteries to ensure, larger batteries to ensure to get seasons worth of data out of them. So as we developed the time domain reflectometry measurements, there's also a need seen to try to improve on some of the problems that I've just mentioned about that. And some of these have been addressed through capacitance or FDR frequency domain sensors, and I'm going to go through and talk about these now. Now, I already talked about the idea of the magnetic field, and I don't know back in that slide if I said it was an electromagnetic field. When we have a magnet, of course, it's a magnetic field, not an electromagnetic field. When we have a battery or some kind of voltage source and can produce a field over these two electrodes, of course, now we call that an electromagnetic field. And we have one here on this slide that I've shown. This is the standard capacitor. Go to your physics book. You can get a very similar diagram out of there. We have two plates, a positive plate and a negative plate. We have charges, a difference of charges across those two plates. They form this electromagnetic field you can see in red here. And whatever's between those two plates will briefly store that charge. And we use this very effectively in almost all parts of our lives, in what we call a capacitor, as I've already mentioned. Now, the reason these sensors are called capacitance sensors is that they basically use the same idea as a capacitor, but do some things with it to improve it, to use it in soil. So let me show you what exactly is going on here. So instead of two plates, here in this picture, we have our plates parallel to each other in the same plane. Now, say this was pushed in the soil. So what you're looking at here is actually a sensor. Maybe we can look at this one down on the bottom of the slide. We turn those prongs so we're looking directly in line with those. We have those now sticking in the soil where we have water around them. And this water that's surrounding the probes, if we produce an electromagnetic field around in this soil and water, then those water molecules actually will line up in that field briefly and store some of that charge just briefly there that we produce in the soil. Now we can relate this charge storing that our sensor now measures through this technique to volumetric water content, and much the same that I've already described twice. But here we have the sensor output, this charge storing ability that the sensor measures, and the volumetric water content. And in this relationship, we just so happen to have a linear relationship between the two. Now here we have several different soils. We have a Houston black clay, which is a very heavy clay, highly charged clay. We have a Palouse loam. We have a Patterson sandy loam, and just a fine sand here. We put them all into this graph to just show you a little bit of the relationship you can expect when you put a lot of these sands together, a lot of these soils together, and look at their different relationships between the sensor output of a frequency domain sensor and the volumetric water content. We can see that we have a fairly good relationship. Now let's talk about the advantages and disadvantages of the FDR or capacitance technique. Now, some of the advantages are that they're lower cost because they don't take a lot of circuitry. Now these can be purchased for much less than many of the other things that we talked about here. Also, because of what I just mentioned, they only require a pretty simple readout device, and they're reasonably easy to install, although that goes for several of the sensors that we've talked about, like TDR and the dual needle heat pulse probe. One interesting thing about this technique is that circuitry can be made so that we can resolve some extremely small changes in volumetric water content. We know this because NASA came to us several years ago and said, hey, can you build a water content sensor along with thermal properties and electrical properties to go on the 2007 Phoenix lander on Mars. And we said, yeah, we can sure try. And they said, by the way, we want to see if maybe you can sense if there's water there, so we got to be able to resolve some pretty insignificant changes in water. And this is what we came up with for that probe. So we have tested this particular idea, just an interesting aside. Another thing that's very nice about FDR sensors is that they're very low power. And so different from some of the other things that we've talked about, we can put a very small battery out to run a data logger and have these function for even years at a time. Now, some of the challenges with FDR sensors are a little bit difficult to talk about because there are a lot of FDR capacitance sensors out on the marketplace. So some of the things I say apply to some and not so much to others. One of the reasons that capacitance sensors in particular have got a bad name in some markets is that originally when Clark Topp took on this idea about the charge storing ability being measured with this dielectric permittivity, was that many said, hey, that's great, we'll just put a sensor to be like a capacitor right there in the soil and then we'll make this measurement. Well, it wasn't quite so easy because these measurements they were making were turning on and off that electromagnetic field so slowly that other things were storing the charge, not only the water, but you can imagine that salts in the soil would store that charge, and of course charged surfaces on the soil, the way they interact with water would also change the charge storage measured by some of these instruments. Essentially what had to happen is electronics need to improve. And as electronics have improved, we've been able to make these measurements at higher and higher frequencies and reduced the dependence of these measurements on other factors like this EC and highly charged clays, etc. So as I'm talking about this, we can mention some of these disadvantages, but it sometimes is probe specific. So if you have any questions about how a particular sensor is affected by these things, either try measuring it yourself using a calibration technique that you can find on the internet. As I mentioned, we have one on Decagon's website, or ask the manufacturer. So as I say, some sensors are sensitive to soil texture, some are also sensitive to electrical conductivity, maybe temperature changes for some of the same reasons that I mentioned, but it really depends on probe measurement frequency. Some of the problems with these sensors is that we also can have the difficulty of installing them downhole, which is kind of a pain sometimes, but there are some good techniques that you can use. We'll talk about that in a minute. And some sensors, well, not some, all sensors that measure dielectric permittivity, TDR, FDR, all of them are sensitive to air gaps because, as you remember, I mentioned that this electromagnetic field that's formed is strongest right near the surface of the sensor. And so if we have air gaps between the sensor and whatever we're measuring, as long as it's not air, then we've got problems. Okay, let me just briefly mention this fact that there are some limits to dielectric measurement accuracy. I already pointed them out. Things like temperature. Temperature can change the availability of water to be polarized in the electromagnetic field. And there are a lot of papers that are written out there on this subject. And I encourage you, if you want to know more about it, to look out there, or as I'll talk about at the end of this presentation, jump on a forum and start a discussion on the fact. Also, as we already talked about, polar molecules in the measurement field, in that electromagnetic field, can change how charge is stored and therefore can change that relationship between the sensor output and water content. Now I got to make a little note here that particular issue, the electrical conductivity, does not apply to measurements using time domain reflectometry because it tends to be insensitive across a wide range of electrical conductivity up to a point where there's so much salt that no reflection comes off the end of the probe. Okay, let's jump into the topic of permanent installation, installing your sensors into the ground. And my colleagues here at Decagon have made other presentations that really go into detail on sensor installation. And there's even a nice video of some field work showing you all about how to install your sensors in the field in the way we did it when we put together a scientific experiment we're running out at the Cook Experimental Farm here near Pullman, Washington. Now look at that video if you need that information, but let me talk about some of the ways that I've just worked on myself or I've seen out as I've traveled around and worked with people installing sensors. First of all, one of the most common ways and the way we did it back in the very beginning, we just dug a pit, stuck sensors carefully, vertically, like this, right into the sensor wall. That's the first technique we used. But obviously there are some challenges with that technique. There's a lot of effort involved. Sometimes the cables that come out of your sensors going horizontally that need to go vertically can break the strain relief and other things of your particular sensor. So there was a concern over that technique and we started working on other ways that might be better. Technique number 2, dug a 5 centimeter auger hole, or augered this hole down to the bottom. We put the sensor into the bottom of the hole using a PVC pipe, pulled that pipe out of there and then carefully backfilled that hole. Now that technique, it's actually discussed in this video at the bottom of the page. That was actually pretty useful, but there are some concerns and some things that we don't like about that. And I've seen some other techniques that might be just as useful. Number 3, for example, augered a 10 centimeter auger hole and then used a device that they had crafted themselves to actually turn at the top with the screw, and that basically shoved the sensor into the side of that 10 centimeter borehole or auger hole, which ended up being a very good technique for those guys to use. Finally, other techniques that I've seen, actually augering in at a 45-degree angle and then inserting the sensor at the bottom of that hole. Why 45 degrees? Well, because there is a concern that if you have your cables running running straight up to the top of your hole, that it might allow preferential flow of water down the cable and down that newly formed hole and essentially change your measurements. And if you run in at a 45-degree angle, there will be a lot less likelihood of that happening. One thing to note, I already mentioned it, but I'll say it again because it's pretty important. If you have a flat side to your sensor, please think about the fact that you probably want that flat side vertical, because if you leave it flat, you may actually pond water on there. My first experience with that was a pretty funny one. I was testing some of the very early echo probes that Decagon made. Just as a new, fresh out of school graduate student, the new project, we developed these sensors and I was out there trying them out. And one day, my sensor, even though I was watering the garden where it was, just really stopped giving the really nice range that I thought it should. And I was scratching my head for days. Went out, dug up my sensor, and while the top of the sensor looked great, it wasn't ponding water as you might have expected, as I picked up that sensor, and it was an old, flat, long sensor like this, a worm had completely excavated the entire lower soil area underneath the probe, and it was just sitting in air. So that's something for you to think about as you install sensors. Use a little common sense. I didn't. That's just a little help for you as you're doing it. Another installation technique that some people use is what we would call a push in and read technique, where you just take the sensor and a readout device, you go and stick it in the soil and read what the water content and any other thing that the sensor kicks out, read what it says. Now, this you can use for spot measurements of water content. A lot of people want a ground truth measurements they're making, sometimes from that Cosmos system that I mentioned earlier, or other types of measurements that are being made maybe by satellite or other things, and they would just want to go and poke in sensors around and make measurements. You can do this. The technique is simple. All you have to do is just go push in your sensor, read it out, store the data somehow on the instrument or with a piece of paper, and then move on and make another measurement. My concern with this technique is not the way the measurement is made, but just the validity of that measurement. We spent a lot of time here just having fun looking at how water content varies in space. And in fact, if you go out, take a long tape measure, lay it out, and measure water content, let's say every half meter across a long transect, you'll find you can create a very interesting variogram, something that tells you the variation in water content across the length of this. And you'll find that soil moisture does just naturally vary across distance. And trying to go sample out in a field with the push and read method may give you more of the natural variation in the soil moisture there than the variation over time in what you're particularly interested in seeing as this develops. So it often comes to me, hey, what should I use in my experiment? What technique is best? Well, my answer is always, it depends on what you're trying for and what you want. Now, every technique I've talked about has advantages and disadvantages, and you can get volumetric water content, or even gravimetric, of course, from that technique. And so it really depends on what your goals for the experiment are and several other things. What experimental needs do you have? How many sites? How many probes at each site? How far away are they located from each other? What is your current inventory? Do you have a pile of sensors that some other professor or you used back in the day that you can recycle and start on this new experiment? What budget do you have? You know, if this is on a grant, there may be a lot of budget to buy sensors, but a lot of times these things are done on a shoestring. So how much money can you spend to get the data that you want? What is your required accuracy or precision? Now, a lot of the stuff we talked about, really with good technique and good understanding of the theory behind what you're doing, you can make very good measurements. You can get good accuracy, especially with a soil-specific calibration. But it's something to think about. If you're just wanting relative values of water content, there actually are a lot of ways you can do that and not spend very much money at all. Maybe make your own. But most cases, we actually want good values of water content that are reportable in the literature and have a reasonable amount of accuracy. Another question for you to ask is, what people power do you have to actually go do the measurement? Maybe if it's the gravimetric sampling technique, or if we're going to use neutron probes, you've got to have somebody or several somebodies dedicated to go make these measurements day in and day out, especially if you want very good frequent measurements of what's going on in your field. So that's really got to be a consideration. And finally, certification. If you're going to use a neutron probe, obviously you've got to be certified to be able to use that technique, and so that's going to take some time and create additional hassle for the measurement. But sometimes that's something that is a good thing to use. Now, just to kind of finally finish up this presentation, I want to take you through some of the applications I've experienced. And of course, I can't run the whole gamut, but these are just things I've swept together and said, okay, here are some of the typical ones. Try to take a specific case out of the typical ones and give it to you. So here's the first one. In this case, they want to do some irrigation scheduling and monitoring. So they had several sites across a relatively spread out area where they were wanting to make measurements from relatively near the surface down to pretty deep in the soil. What they were wanting to see was where the water was coming from, how much water, what the water status down well below the kind of irrigation zone, what was happening there, to see if maybe they could tell if water was increasing down there. They wanted to measure this continually, so they had a continuous record of water content. They had money in a grant available to do the monitoring, and their overall idea was to take this system as kind of a pilot system and then roll it out to several areas where they could actually monitor and control irrigation. And the best idea from them was the FDR capacitance sensors. These have good accuracy, they're inexpensive, very easy to deploy in the soil, and they can even use radio telemetry or cell phone technology to bounce all that information back to a central point or even directly onto the internet and onto their computer. Second case we can talk about is plot monitoring. This was an interesting case because you say, hey, wait a second, that's very similar to the last thing that you presented. Well, it's not quite. It differs in one very important detail. These were plots that were closely spaced together, 4-meter spacing, where they were just looking at some particular aspects of the plants that were growing in these plots. And what they wanted to do was just monitor the soil moisture at several depths in these plots and look at what changed over the season. Now, they had a requirement that they would measure daily, no more than daily. They wanted that record, but they didn't figure that any more would be helpful. They had very limited budget, which was a bit of a challenge trying to decide between the different things that they could do. But they had labor there that they could use on the experiment. Now, their best decision, I thought, was a neutron probe because, of course, they're accurate. We showed some of those data in that section that we talked about. The price is only the price of the instrument. So if you pay that price, you can quickly get back and not have anything else to buy. You can use that across the whole field. This measures at multiple depths and at multiple locations, which is fine, and these instruments are very reliable. So they had somebody available to do the work, and the neutron probe was the best choice there. The third case was an interesting one, and I already talked about this push in and read approach and my concerns with it. So immediately when I talked to the person on the phone and they said, hey, I want to do a geostatistical survey of the catchment water content, I want just to go stick in the probes at a lot of location and look at statistically significant areas in terms of water content across the catchment. I have literally no budget for this project. I have people available who I can send out and do, or send out student workers who can go do the work. And variation is key to my analysis. And immediately my knee-jerk was just to say, well, you're just going to see the spatial variability of water content that just naturally occurs anywhere, no matter what you're dealing with. But they said, no, you know, that really is crucial to my analysis, and it is going to vary based on a lot of the things I want to measure. And I thought about it, and of course they're right. That was a good approach to doing this, as long as variability is something they're focused on, and they're not going to be surprised at the end of the experiment when they see that there is a lot of spatial variability that tries to wash out some of the temporal variability. So the decision for them was a nice push and read sensor where they could just walk around in the field, make the measurements, and not have to leave anything out in the field that they would maintain or have to install like a neutron probe or something like that. And finally, ecosystem water balance. And this is probably the most typical application that we get for sensors, at least here at Decagon, which is where people are wanting to study a whole ecosystem and the water balance or many aspects of water in the ecosystem. Now, this is a little unique because what they wanted to do was set up a central location. They wanted to very intensely monitor right near this meteorological station where they probably even also were measuring eddy covariance and other things to get CO2 flux, etc. So they wanted to really intensely monitor there where they could put more expensive data loggers and connect everything up together. And then they wanted to put lots of little stations around where they can kind of evaluate lots of things going on rather inexpensively at remote locations. And their decision was pretty simple, actually. The central location, you want to be able to use TDR or some of these multifunction probes where you can measure both the water content and the electrical conductivity. And I forgot to mention actually in the TDR discussion that not only will TDR give you water content and is insensitive to EC, but you do get a measurement of electrical conductivity out of that signal as well. So TDR or a multifunction probe, multifunction probes can measure electrical conductivity, temperature, and water content together, but they tend to be a little more expensive. So those could all be located around that central system. And then outside that, put FDR capacitance probes at small little installations that covered around, maybe hook them up by cell phone or by radio, and then get them all coming back either to the central location or directly back on the internet to a computer. So that was the best, at least in my opinion, the best way to handle this particular project. So in conclusion, we've been through a lot of thoughts and ideas. We've talked about the theory behind a lot of these measurements. I know that we didn't have time to really get into some of the gory details, but I hope now that you understand at least the principles behind everything that really is out there to measure water content at this point. And you're able to take that and make a good decision when you think about installation, when you think about applications. Now you should have the background to at least start on moving toward what you really need to meet your particular needs in measuring water content. Now, there are a lot of resources available still if you're not quite sure what you need. First of all, I'd encourage you to go on manufacturers' websites. A lot of people who are selling water content sensors will have pretty good information on their website. Now, be aware that you're going to have to do some of your own testing sometimes to make sure that what they have for you is exactly what you need. But in my opinion, calibrating your water content probes before going in the field is always a great way to start, because there are no surprises when you actually get out there and start trying to make measurements. You already know, if you've calibrated, all the things that your sensor does and what to expect in the field. Now, there are other opportunities to actually discuss some of these things. There used to be a lot of water content forums. I've kind of gone out on the internet, poked around a little bit, and not been able to find anything going on actively like there used to be. But Decagon has set up a set of forums that you can go and talk about soil and moisture and a lot of other things. And I'd encourage you to go to decagon.com/forums, and then you can join in the discussion. And I'll be on there. There are a lot of other scientists here at Decagon who will hop on there and answer any question about measurement that you have. And please come join the discussion, and maybe there's something you can understand from there. And finally, give me an email, or any of us here at Decagon. We're happy to talk to you. You can just email support@decagon.com, and you'll, right at your fingertips, you'll have a scientist who's been out in the field making these measurements, can help you get better water content measurements. I hope you've enjoyed today's seminar. It's been a pleasure talking about something that I have a lot of fun with, that I've worked with for many years now, and hope that you can make great measurements in the field.